All right. My clock show that it's 8 p.m. GMT, and it means that it's time to start our regular webinar series about vector symbolic architectures and hyperdimensional computing. So welcome everybody. So this is the last event before Christmas, and I have a pleasure of inviting Mohsen Imani from UC Irvine and Michael Hirsche from ETH Zurich to give this final webinar for this year. Before I leave the floor to Mohsen, the first speaker, so I want to tell that if you have suggestions about talks in 2021, so please drop me a line by email. So I already received a couple of suggestions from Ross and Dennis. So, but if you have ideas of what you want to hear from we can contact to give a presentation, so please send me a message. But now I should stop talking and I leave the floor to our first speaker, Mohsen Imani from UC Irvine. So Mohsen, please.
Thank you so much for the introduction. So hello everybody, I hope everybody is staying safe and healthy. So I'm Mohsen Imani, Assistant Professor from Computer Science Department at UC Irvine. So this is a pleasure to present my work today. So my group is working on an idea of using hyperdimensional computing to perform efficient and robust learning. So my talk is a little bit high level. So I'm going to give some overview about type of work we are doing here in UC Irvine, and I'm happy to take your question right after that. So as we all know, like a human brain and today's computer, they have multiple differences. Like one of the main differences is power or energy efficiency. So as we know, like today's computer, they require like, I can say like kilowatt or megawatt to train or perform a learning task, while this learning task they can perform with like about 20 watt in today's brain. But the only difference is not power or energy efficiency between these two computing paradigms. Like robustness is another important factor. So as we know, today's computer, they rely on like switches, transistors that they are working. If one of the switches they stop working, the entire system may crash. While in human brain, like when I'm giving talk even, I may lose thousands of my neurons, but I'm pretty accurate. The other very important factor is about parallelism. So the brain consists of 100 billion neurons that they are connected together in a sparse way, and they provide highly parallel computation. But the amount of parallelism on today's computer, it is limited by the number of cores. And we all know this is a best case scenario. In many cases, we cannot even utilize cores because of the memory wall or data movement issue. And the last factor is about learnability. So the brain is learning from both supervised and unsupervised data. While today's computer, they don't learn, they emulate the learning in very inefficient way. So this is obvious that it's a time to rethink computing. It's a time to design computers that can natively support learning tasks. So what we are doing using hyperdimensional computing, we are looking at how the brain works from abstract and functionality level, and we are trying to mimic the same properties on a hardware. So what are those principles? There's multiple principles for any brain computing model, but one specific actually important factor is that brain doesn't have separated memory and computing unit. In fact, in brain, the memory and computations are interconnected. That's the opposite way we try to design computer for a while. We try to make memory and computation separated. Also, like robustness is very important because new technologies are becoming like our neuron in our brain. They are pretty noisy, but brain is working well to perform learning tasks, while today's computer, they are not robust to such noise and failure. So we need an algorithm like a brain that can provide that robustness. So let's jump to the HD hyperdimensional computing or HD computing part. So if I want to use HD computing to perform learning tasks, this is the overview. You have a bunch of images of cat and dog as an example, and you want to do classification. So our method, it mapped the information of these cats and dog into high dimensional space and represent every cat and dog using vectors with 10,000 dimension. And this is the training part. In the inference part, when the new input comes, we map it to high dimensional space, and now the computation is similarity search to search if this query is more similar to the cat or dog. But the application of this method is not limited to image or classification, regardless of data type. Our group, it tries to actually perform different encoding methods, which can map the different data types into high dimensional space. Then we perform different learning tasks over the encoded data. Like we have designed different libraries that some of them are open source and some of them they will be, that how you can perform classification, clustering, regression, reinforcement learning, or even cognitive tasks over encoded data in a very native way and very efficient way. So, but what's a like main advantage we have in hyperdimensional computing in terms of learning process? First thing is that we are highly parallel. We support lots of bitwise operation, and we are very memory centric. So it's kind of ideal for today's hardware or even emerging hardware. Also, we have a lot of robustness to the noise and failure. So if you're running it on hardware that may have like about 30% even random noise, we can have a robustness and we can provide completely accurate learning result. And lastly, it's about fast learner. So any algorithm we develop, we consider to be kind of single pass. It can look at training data point only once and it create a good model. So you know the mathematics better than me, but I'm gonna just give you very like a high level overview about like basic math we are using to perform like a learning task using HD computing. So the first operation is bundling. You know, if you have some high dimensional vector, if you bundle them together, like get majority over them, it is like a memory. Because if you check the similarity of H with vector which is in a set, it says that I have it. And if the vector is not in a set like V4, it says that I don't have it. If the vectors are in high dimensional space. And of course, if they are randomly generated. And what's the capacity of H? That's a very important question. I will answer it later. But I believe if we can answer this question mathematically, we can solve lots of problems and we can like make HD more kind of with more mathematical. Like we can actually give more knowledge to users how to use HD computing and which problem they can solve. The second operation is about binding, which is association. If you have two random vector, if you just multiply them together, you kind of bind them together. It's like XOR operation in binary that you generate a new vector, like apple and red, you bind them together, you generate a new vector which is orthogonal to both apple and red, but it's invertible. And the last operation is a permutation. You do rotational shift of a random vector and you generate a vector which is nearly orthogonal to original vector. And it's good for representing sequence. So if you have ACG, 3 characters, you can bind them together to kind of associate objects or 3 characters that each of ACG, they are a randomly generated hypervector. But that doesn't remember the sequence, so we can assign a unique permutation to remember the position or timing to, I can say sequence, like I can sequence which one happened in which order. Similarly, if you go to time series, like one more example, like we generate if I want to encode like windows that I show here, we generate a random vector for ymin and ymax, which is minimum and maximum value my signal can get. And after that, we do vector quantization to generate a vector representing each intermediate y. And now the encoding can be this one. It can be binding operation between y's and permutation to preserve the position or timing. And if the windows shift ahead of time, we can actually do vector quantization again. We can generate a new encoded vector for H2, which is second windows. And now we can memorize all these patterns together. If you look at here, I don't have one H, we have a lot of H, but this memories bundling that I explained, it is like a memorization. So it can generate a pattern that remember all these patterns of the windows we had. So a more complex example, if you have like cat and dog, you can actually perform encoding method, which maps every cat or dog into high dimensional space. And now your learning task, it can be as simple as a bundling operation. Because as we know, bundling, it remembers the information of all these patterns into a single vector. So in fact, we can perform a learning task in a one pass. If the new input comes, I just encode it and bundle with the existing model. So with no gradient operation or backpropagation, which enables us to do online learning. But just a challenge is that, what is an encoder here? So that's a bit, it's very challenging question, because that can be supervised, unsupervised encoder. Of course, we would like to go with unsupervised always encoding method, which we can actually like remove the cost of training phase, which we usually have on deep learning or neural network. But this is a question that you may want to look at some of our recent paper in order to see how we answer that. I'm not going to cover it here. And if you compare the accuracy of like hyperdimensional computing based on our novel, I can say new encoders we have, you can see we provide comparable accuracy with like a state-of-art deep learning method. Not for every data type, but with most of the data types that like they are like feature extraction, text, time series, and so on. So for tasks like image or video, we are losing more accuracy because our encoder, it's not trainable. So, but like, even if we are losing accuracy a little bit compared to deep learning, the advantages that we provide, they are pretty interesting. If you look at the graph at here, bottom left, the blue line, it shows the accuracy of hyperdimensional computing. Red, it shows deep learning, deep neural network. And you can see in different like epochs or training iteration, like our accuracy, they start converging faster. And also we start, that's a very important, we start like the accuracy from a value which is really high. So we don't like, unless neural network that they start with something like a random. So this is actually enables us to provide a really good accuracy in one pass without performing any iteration, while we are performing highly parallel bitwise operation to perform learning tasks. So no complex operation. And all these features make our approach promising to perform learning tasks on today's embedded devices, that they don't have enough storage to keep the training data point and do iterative learning. Also, they are battery based. They don't have enough resources to do complex gradient-based learning. Also, it is very promising for future technology. As I pointed earlier, today's devices are becoming very unreliable, but hyperdimensional computing, it has holographic distribution in high dimension and redundancy, which enables us actually to work very accurate, even if we lose a lot of these dimensions. This is making our design kind of promising for future technologies, that devices, they may have noise and also failure. So let me point a little bit to the limitation of HD computing. So one of the main limitations is that, like, if you remember, I mentioned that when we encode the information, it can be any data point. This is just image here. You generate a vector for every like input data, and we bundle them together to generate a reference hypervector. But if you look at what is the capacity of the hypervector R to store the information of H, so that capacity depends actually on two factors. So if you look at the top, it depends on how orthogonal are these H together and what is your dimensionality here. So you can always increase dimensionality, but it comes at a cost of like efficiency. But the orthogonality is very important. And unfortunately, most of HD computing encoders now, they are very exclusive. They map information into high dimensional space such that these H's, they don't have similarity. So this is good, you know, if you want to perform exact match, like in R, but if you want to do approximate learning and computing model, we will have like capacity issue. Like, let me show you how like this design works. Like if I have a model R and I want to see if R, which is my memory, it memorizes all these H, I can actually perform a similarity search of a query with the R here, and I can see a term which is identical. Think about Q is H1. I would have a term which is H1 and H1. The cosine similarity will be 1, and I would have a lot of noises because these H's are nearly orthogonal. So, and as you can see in the bottom figure, you can see the orange actually distribution, which is Gaussian. It is showing the noise, and the noise, you can see it's becoming wider when we actually store more patterns into a hypervector. P is increasing, you can see here. It means that we have more terms stored into the R memory. So, and as if you like, we actually have a complete I can say mathematical, statistical model for HD computing to see what's the capacity of hypervectors. You can refer to our paper here at the bottom. And we can see that the capacity is pretty low because these vectors are nearly orthogonal. So let me go and maybe show the same problem in a different way. Like, what's the problem? Problem is coming from binding mostly, and also permutation. But let me point to the binding operation. If you have like apple and red, if you bind them together, you generate H, which is red apple. And as I mentioned, H, it is orthogonal to both apple and red. So this is very exclusive computation. Of course, we need to be exclusive, but that is kind of decreasing our capacity too. This is a trade-off we have. Let's remember let's think about we have a memory with lots of objects in high dimensional space. What are those objects? Let's take a look at two examples. Like I have sun and I have ball, which they have features of shape, color, and temperature. You can see even sun and ball, they have similarity. Two features are same, just one feature is different. But if you look at the sun and ball, they would be nearly orthogonal, meaning that they will decrease my capacity of learning in a memory here. So this is really good for exact match, but it is not good if you want to perform approximate match, because we cannot preserve similarity of the sun and ball in a memory here. If you go to the inclusive encoder, we can assign a random hypervector to every position, every feature we have. And after that, we can encode the information by actually performing binding operation between the position hypervector, which store the position of the feature, and every feature. It is high dimensional feature, of course. It's a random vector representing like round, yellow, and hot. So as you can see here, if you check similarity between objects, even in a memory here, when you have multiple objects added together, you keep the similarity, because now you remember how many features are different. But again, the problem mathematically is that you are doing lots of bundling operation here. You can see you have a lot of addition here, which every bundling here, it decreases your capacity. In fact, this model, it can do approximate match, but because of a lot of bundling operation, it doesn't have enough capacity here, because this bundling actually it has been repeated here. So this cannot even do exact match too. So we should know about that. It's very low quality in order to do exact match. But what we are developing here at UC Irvine, we are actually developing a correlative association, which enables us to perform as simple as operation, like a binding operation at the top, like here, exclusive encoder. But at the same time, we can do approximate or exact match. So we are mapping vectors to another space that can keep the correlation of the vectors in high dimensional space. So I'm not going to details of that. I just wanted to give you a high level about this. This is our ongoing work. But we are observing very interesting results, because this is actually working like attention memory for us. So we can actually specify with one simple search, we can say if it's exact match, if it's approximate match, and even if it's approximate, I can tell you which features are different. And they're all happening by one search operation or reasoning. And just to show you some our initial result, you can see if I'm doing approximate match, this is a capacity I have based on number of dimensions and number of patterns that is stored in like hypervector, memory hypervector. You can see here that when I'm doing approximate match, exclusive encoder, as we expected, they don't actually preserve any similarity to do approximate match. Inclusive, it is good, but the capacity is low. You can see there's a lot of red part, which means that our probability of finding is very low. But if you look at our correlative one, it has really high capacity in order to do like approximate match. This is the same scenario for exact match too, which I didn't show it here. So, but what's the application of that? You know, of course, the application of this memorization, it can be on learning tasks that I cover, but I want to show that the only application of HD computing is not there. We can actually use HD computing for pattern matching. So if you look at a pattern matching, it looks like a brain like memorization. You have a really large human reference genome, and you have a query. You want to see if query exists on your memory, that you actually store this pattern. So of course, you can do it on original space as the existing algorithm, they work. But what we are trying to do, we are trying to map this information into high dimensional space, we bundle all these patterns, encoded patterns here together, and we generate a vectors or new library in high dimensional space that we can perform similarity search on data space now. Like you can see plus and minus one for black and white, for example, box, they show +1 or -1, for example, or they can be multi-bit values. So just to show you how our approach works, like usually the query lengths are fixed, like think about 200 DNA lengths. And we are breaking, actually, we are getting a part of like reference genome, and we are breaking it to the same size queries. And after that, we encode every query into high dimensional space, and we bundle them together. So we generate a single vector that it represents maybe thousands of patterns. And that 1,000, it really depends on capacity that I talked before. If all these vectors are nearly orthogonal, I don't have enough capacity here. So it might be 500. But if these vectors, I keep the correlation between these hypervectors, I can store more of them into a bundled vector here. But regardless of that, one vector, it represents too many patterns in original space. So one similarity search, it is equivalent to, for example, 1,000 patterns matching in an original space. So this is actually giving us some kind of feature in order to do extensively parallel similarity search on like existing hardware or new hardware, which give us actually performance improvement. Just remember this, our framework is not as simple as I explained. Here we are actually having some retraining method, which tries to actually adjust the pattern in HD library. So, but you can refer to our date paper last year, 2020, which is this year actually. So depending on the encoder, we can perform exact match or approximate match. So, but like here, I'm just showing the results for exact match where our encoding is very exclusive. You can see depending on the patterns that is stored in every hypervector, I would get different actual percentage of error during similarity search because bundling does not come free of error. You kind of lose a bit of information, but we show that this error can be very minimal depending on stored pattern in every hypervector. And if we run it and we compare it with the state of our algorithms running on GPU and FPGA, and we see that we are getting about 44 times faster computation on both GPU and FPGA because of parallelism and actually limiting the data movement we have in our like architecture because of our memory-centric feature here. So I'm moving a little bit to the hardware part now in the remaining minutes I have. So in today's processor, we have like a CPU which is doing a great job on performing precise computation. Next to that, we are designing a new processor with name of high dimensional processing unit, which is like a cognitive processor for us. It can perform different learning and cognitive tasks based on hypervector, which is a common data structure we have. Like CPU that they work with integer floating point, here everything is like hypervector for us. But the question is that where should I implement this HPU here? Is it CPU, GPU, or any other hardware? And the answer is that it can be anything. So it can be your CPU, it can be GPU, and so on. So during last few years, I can say last 5 years, we have worked on different hardware implementation for HD computing. Specifically, like we are working with like opportunity of using ARM Helium in order to do vector extension in hyperdimensional computing. In GPU, we are looking at how we can accelerate hyperdimensional computing on TensorFlow or PyTorch recently. And but we know that this is not an embedded device, but it is a really good tool for that we can release in order to community. They use it in order to develop HD computing codes and different algorithms they want to map. And this, in terms of FPGA, we have done actually, we designed different frameworks, like automated framework that can get your code, like a C code, and it can automatically translate it to any Xilinx FPGA. And also we have a very optimized implementation of HD computing, which can be a general algorithm you implement using HD computing on FPGA. So example is our HPCA 2021 this year, which just accepted, but you can find our other papers too here. But if you really want to get advantage from HD, like we can go to ASIC design or doing processing in memory, because like we have a memory-centric feature And we can exploit those features in order to enable approximate computing and highly parallel computation, which is required in order to process HD computing. And example of, so we have done actually a lot of work in order to design new hardware platform for HD computing for last 4 or 5 years. And we have even a fabricated chip based on that, like we verify the functionality of some basic operation there. So, but our recent work, like in Macro 2020, it kind of show more general overview of our design in our computer architecture venues, how we can actually use HD computing to revisit other existing algorithms in order, like unsupervised learning algorithms, in order to run efficiently in HD space. So one example of like kind of computation we have done before, which was like a few years back. So it's about how we can perform nearest search in hardware with name of content addressable memory, which is kind of lookup table for us. So we have different patterns which we store in the different row of lookup table. They can be pattern of cat, dog, rabbit, and so on. And when query comes, we want to check the similarity of query with every line. So in order to do that, we cannot use content addressable memory directly because they just support exact search. What we have done, we added one transistor to every line, which is this transistor is connected during search. So it fixed the voltage of every green line here to VDD during search. Depending on number of mismatches that query has with every line, the yellow cells, they show mismatches. You can see they don't match. These start discharging a green line. The more mismatches, the higher current passing through access transistor. So by adding a current mirror and current comparator, we can find a row which has minimum discharging current in access transistor. And since we are approximate, we can actually use the LTA current comparator, which is loser take all, that we are pretty approximate too. We don't need to do exact implementation of that. And we show like really interesting result there compared to the ASIC design and also compared to the GPU, which can be orders of magnitude faster. And also we have like a recent effort in order to design a chip based on, I can say, ferrofet devices, multi-bit ferrofet devices in order to support exact search operation. Now our goal is actually in collaboration with Professor Kai Ni at Rochester Institute Technology in order to actually enable nearest search or other HD operation using these technology files. So actually we can refer to our work in IDM 2020 this year too, that we have chip fabrication for exact search operation using this technology. But going back to the efficiency of HD computing, actually robustness of HD computing. So as I mentioned in today's processor, if one of the transistor it fails, the entire system may get a failure. But in processor based on HD computing, if devices, they stop working, it is like aging in human brain. So this is actually our simulation that it shows the quality loss, which is accuracy actually, kind of quality loss of regression and classification when we are using a processor based on non-volatile memory for a few years. And you can see after a few years of using chip, we start losing accuracy, but we don't fail. And this losing accuracy is because the devices are like our neuron, they stop working. But interesting part is that we start losing accuracy much faster for regression than classification. What does it mean? It means that if I become old and you ask me, what is the temperature in a house? It is like a regression task. I may have some difficulty to tell you exact temperature. But if you ask me it's cold or warm, it's a classification, I can answer you. That's exactly what we are observing here too. For the same task, we may lose more accuracy for regression rather than classification. But this robustness that we are providing, it actually is promising solution for many different computing paradigm today that we are doing. We are going to dark silicon, near threshold computing, deep nano scale technology, that they are all adding some kind of error or inaccuracy to the computation. So we can be completely robust against those failures. And the last slides that I have, it's about like HD computing in IoT system, which is one of the active projects I'm doing at UC Irvine. And it's about how we can distribute the learning task over different devices using HD computing. So the problem that we are looking at that your general IoT problem, example is a smart home project where devices are generating heterogeneous data, not homogeneous. And our goal is to distribute the learning and training task, not inference, uniformly over every devices. When I say uniformly, it means that we distribute it based on capacity that every node it has. So a part of like training happens on house two, a part in city, a part on TV, and so on. So like this is kind of impossible problem to solve in deep learning. It's a really complex model because breaking neural network in training phase in heterogeneous actually scenario, it's really hard. But like what we can do, HD computing is mathematical. We can mathematically estimate the dimensionality, and we can aggregate the result through the hierarchy of devices such that every node it carry out a part of learning task. So that's type of work we are doing, and we are observing very interesting result in kind of some implementation we have and simulation we have too. But besides these features that I explained, we actually observe very other interesting features about HD computing too. One is about security of the learning task, which we are collaborating with Intel on that. So we are looking at if we are sending information to a cloud, can I assume HD data, it is secure by itself? Like if I have multiple users sharing information with the cloud, can I make sure all users, they use different bases, like different definition of alphabets, but cloud can still combine the information together? The second question is about like features, which is interesting, is about invertibility of the encoder, which can give us some further feature in order to go back and look at the model and see why some of the predictions it might be wrong or it may not make sense for us. So it can give us interpretability. And lastly, it's about robustness, which is very important factor in terms of robustness on every node, because nodes are sometimes battery based, they are unreliable, and more importantly about the noise that we may have on a network, because during even like transmission, we may lose some of these packets. But if the information is in HD like format, we may not lose anything in terms of like final accuracy result. So it gives us another like level of robustness in IoT systems. So I think I want to conclude my talk now. Thank you so much for attending my talk, and I'm happy to take your question.
Thank you very much, Mohsen. So our applause to you. So we have several minutes for questions. So please unmute yourself and speak out. Well, maybe I can start while other people are collecting their thoughts. Mohsen, so you mentioned that, I mean, you're in the beginning of the presentation. So when you discussed the trade-offs between the capacity and the encoding techniques, so as the motivation for developing this correlation preserving encoding, so is to encode similar objects similarly, so to say. But in supervised learning, in many cases, you want to separate similar objects into different bins. So what would you suggest in this case, based on your experience?
That's a really good question. So actually, it is a really, I can say it's a trade-off. Like, you know, the capacity that you can perform the learning task, as I mentioned in my slide, it really depends on like how similar are objects when you're mapping them into high dimensional space, and what's your capacity in the memorized vector. So ideally, I would like to have infinite capacity. I increase my dimensionality in hypervectors, and I map everything to orthogonal space, as you mentioned. So in that case, I can perform the learning task. But the problem is that the capacity of vector, even in practice, it doesn't increase linearly with hypervector. After like going a little bit higher dimension, our capacity will be saturated. So that doesn't give us any actually rule, rather than just going back and just trying to make sure the vectors that we are generating, they have some kind of correlation. But to avoid the problem you mentioned, our encoder, we believe it should be unsupervised encoder, not a static encoder. It should be unsupervised that look at all the training data points, and it kind of understand the correlation between them in original space when it's mapping them into high dimensional space. So in that case, we wouldn't actually face the kind of problem that you pointed to somehow. And we can actually, but we will pay the cost of like unsupervised learning of the encoder, but we can make sure we can map HD computing to more complex tasks where we really want to actually separate data points together. So our encoder, in fact, it will try to learn the representation of HD by itself.
All right.
Does it answer your question?
Yeah, no, definitely. I think if I have other thoughts, I can
Awesome.
contact you offline. Definitely. Other questions, please?
I have one question. So Mohsen, did you compare your empirical capacity results with the theoretical, the theory as in the Frady et al. 2018 paper where you could actually compute theoretically what the capacity would be, and also for your DNA example, how does your method compare to the state of the art in competitor methods?
That's a really good question. The first question, we haven't tried to compare with other approach yet. And the reason is that it's an ongoing project. We are just trying to develop something, and we have a good implementation, but we haven't go to the phase of like comparing with state-of-art models, which I believe there are quite a few models there. But that was good to hear, like your suggestion about that. Thanks. And about your second question, I can answer it in this way. Like what we are supporting in DNA matching now, it's exact matching or approximate matching. But some of the state-of-art algorithms in bioinformatics, they require to solve alignment problem, which alignment, the distance is different from an exact or approximate match because it needs to take care of like insertion or deletion. So what we can, like what's the overhead of our approach currently is that we need to actually extend our exact or approximate to go into alignment problem, which we need a few more steps to do computation based on that. So we believe even using that like kind of, I can say post computation, we are going to be efficient, but we haven't tried yet. So our focus was mostly on exact and approximate match, but our next step is to go to alignment problem, which is kind of bigger and more challenging problem in bioinformatics.
Yeah, okay, thanks.
Mm-hmm.